So here we are at the beginning of our last unit. Unit 7 is Earth Systems and Agriculture. It's separated into two distinct parts. We're going to talk about chapters 2, which is Earth Science, a little bit of geology, my favorite, and then we're going to talk about how that impacts mining for 23, and then chapter 23. And then the second half of Unit 7 is going to be agriculture and soil formation. Okay, so that's kind of where we are headed. All right, so let's talk a little bit about geology. This is a short chapter. We are going to go into a lot greater detail on some of the things related to plate tectonics in our key points, but that we can save for then in class. So we're really not going to look at too much between matter and energy, but we're going to talk a little bit about energy. We're going to look at how plate tectonics and the rock cycle have shaped the landscape. And then we're going to look at geologic hazards and how to minimize their impact. So this is the case study. We talked about it in chapter 20. We're going to, the idea of nuclear energy, we're going to talk about it again since it's related to this unit. So we talked about the big earthquake that generated a tsunami. We're going to talk in our key points about how, in more detail, about how tsunami form. It overtopped roughly an 18-foot seawall, a little bit less than 18 feet, that protected the Fukushima Daiichi nuclear power plant, which wound up flooding the emergency generators, which started a meltdown. We're going to watch a video of that was taken in this area, and this is just a picture of a 18-foot seawall being topped by this this tsunami wave. It was that large. This is what happened. So they wound up, the backup generators didn't work because they were flooded. That cooling water started to boil off. You had a meltdown that happened, so that produced hydrogen gas. It spread and exploded, which damaged more buildings. And then in order to prevent further nuclear issues, further nuclear meltdown, they wound up flooding the reactor cores with seawater, and it made things less disastrous than they could have been. So this is what wound up happening. It's an interesting diagram. Your explosion happened in all 4 reactors, and you had meltdowns in 3 of them. So that was not a good thing, to put it mildly. So if we look at the matter that exists in the Earth, you've got oxygen, hydrogen, silicon, nitrogen, and carbon, elements in the Earth's crust versus the oceans. So most of what's in the crust is oxygen and silicon. Most of what's in the oceans is water and hydrogen. That should make sense. In the air, it's mostly nitrogen and oxygen. And in organisms, we are CHON, carbon, hydrogen, oxygen, and nitrogen, with some other trace elements. Some forms of atoms are called isotopes, like we discussed in chapter 20. They're radioactive. And if it's a radioactive isotope, we call it a radioisotope. They do a lot of damage when they get into the bodies of living organisms because they wind up causing mutations. We talked about geothermal in the previous chapter. So the heat that is used to generate geothermal power comes from radioactive isotopes decaying, breaking down, and producing heat, which then melts rock to make magma. Okay, so that's the source of the heat for geothermal power. That magma can erupt from volcanoes. It's the driving force for plate tectonics, the movement of that magma, and it also heats groundwater, which then we use for geothermal heat. There are deep sea ecosystems that are way, way below the penetration depth of light. that are there. So there's like animals, and if there's animals, then there's got to be some production to produce food and energy to move up those food chains and through those food webs. So they use hydrogen sulfide, which is a poisonous gas, to produce sugar in a process called chemosynthesis. So I'm not going to test you guys on the equation for chemosynthesis, but they take carbon dioxide and water and hydrogen sulfide and create glucose and sulfuric acid. All right, so geology. The Earth exists because of geology. Geology is the study of the Earth's physical features, the processes, and history. So the processes lay the foundation for environmental systems, okay? So all of the different environmental systems that we've talked about have a basis in geology. So, and they give it, the geological processes give us resources like metals and fossil fuels, which we need for existence. So the Earth itself consists of layers. You can separate the Earth in two different ways. Okay, at the center is the core, and the core is solid iron, surrounded by molten iron. So it's the innermost layer. Density decreases as you move up from the core. The mantle is less dense than the core. And then at the top is the crust. Okay, so you've got three layers based on density, right? The properties, right? So you've got the core, the mantle, and the crust. If you look at it in terms of chemical composition, so physical properties are core, mantle, crust. If you look at it in terms of chemical properties, you can divide it even further, right? So the inner core is solid, the outer core is liquid. The inner core spins in the outer core to generate the magnetic field that keeps so much solar radiation from hitting the Earth. It also produces the beautiful aurora, the aurora borealis, the northern lights, and the aurora australis, the southern lights. All right. So if you get outside the outer core, you have the lower mantle, right, which tends to be more solid. And then the upper part of the mantle, right, is a little plasticky. It's soft rock. It's warm, but not warm enough to melt. It's under a little bit of pressure. So we call that the asthenosphere, right? It's like silly putty. Over top of the asthenosphere is the uppermost part of the mantle, the coldest part of the mantle, and the crust, right, which is oceanic crust under the oceans or continental crust. They call that the lithosphere. It's thin, it's brittle, it's low density. It's like the shell of the egg, okay? And it covers the entire surface. It's fractured, the lithosphere is fractured into pieces we call tectonic plates, all right? So heat from inside the Earth, that radioactive decomposition that we talked about, creates convection currents that move that magma in the asthenosphere up to force these pieces of lithosphere to move apart, okay? And we're going to talk about that in a lot more detail in our key points. So we can talk about how these plates move relative to each other. That's a study of plate tectonics, right? So this was the Earth about 250 million years ago. We were all smushed together in the continent called Pangaea, Pangaea meaning all Earth. The ocean around it was Panthalassa, meaning all sea, okay? So over the course of time, this convection forced the plates to move apart and to get what we see today. So you've got three kinds of boundaries: divergent, which are these stair-step things; convergent, which are the teeth; and then these straight, plain single lines, which are called transform boundaries. So let's talk about them. At a divergent boundary, plates move apart, they move away from each other as this magma rises to the surface and cools, all right? At a transform boundary, the plates slide past each other, okay? It's like rubbing your hands together if they're cold, and that'll cause earthquakes. It'll cause earthquakes at a divergent boundary too. The third kind of boundary is a convergent plate boundary, where two plates come together. You can get two kinds of motions when two plates come together. depending on the plates that come together, one plate can subduct under the other, which means it goes down into the asthenosphere. It melts into magma, it rises and becomes volcanoes. So this happens when you have oceanic and continental crust coming together, and also when you have oceanic and oceanic crust coming together. The other kind of convergent boundary is when two pieces of continental crust come together. Neither of those pieces of continental crust are more dense than the asthenosphere, so they rise up instead of coming down, and you get really, really high mountains. Okay? And that's everything I just talked about. So, if you look at the connection between plate tectonics and the landforms on the Earth, most of the landforms that you see, the mountains, the oceans, the continents, earthquakes and volcanoes, exist as a result of plate tectonics. So the motions of the Earth's plates have created different habitats, which have then created various types of climates, which have then influenced the distribution of biomes. So it all comes back to plate tectonics, why we have the biomes where we do. Okay, we're not going to dwell too much on the rock cycle because it's not pertinent to what we need to cover. But I need to tell you guys the difference between a rock and a mineral because it's going to come in handy when we get together for our Chapter 23 lecture. So a rock, if you take a bunch of minerals and put them together, you get a rock, right? So granite, like your countertop, is quartz, a kind of feldspar, and mica, typically biotite or muscovite mica. So that's what goes into the rock granite, okay? A mineral, right, quartz and feldspar and mica are minerals. Minerals are naturally occurring inorganic solids with a definite composition and a definite internal structure, okay? So that's exactly what I said. And rocks can get altered through the rock cycle. You guys talked about that at some point in middle school, but it's not pertinent to our curriculum, so we're just going to move on. One thing when you spend any time thinking about geology or dealing with geology, your frame of reference for time changes tremendously, okay? So the Earth has been around for over 4.5 billion years, okay? So geologic processes occur at a much different scale of time than what humans are accustomed to, okay? So we may say, Yellowstone is overdue for a volcanic eruption by 600,000 years, and humans panic and they say, what, 600,000 years? That's oh my gosh, that's so long. Yeah, no. It's not. When you think about the fact that the Earth has been around for 4.5 billion years, it's really not that long of a period of time, okay? So 4.5 billion years is divided into 3 eras and 11 periods, and then the periods are subdivided into epochs. And typically what they do, they determine periods based on looking at rocks. So looking at extinction events like we had talked about earlier, or changes in geology around the world that would give you an indication that there's been some change in the environment. So our current period is the Quaternary period, and it began about 2 million years ago, and our current subdivision of that is called the Holocene. So here we are, right? Pleistocene was before the Holocene, and now a lot of scientists are suggesting that we are now in a new epoch, and we should call it the Anthropocene, because over the last 200 years, we have increased the rates of soil erosion, atmospheric carbon dioxide concentrations, and we've seen an exponential growth in the human population that would be indicative of us heading into a new epoch. And there was a really good book, why can't I remember? The Sixth Extinction by Elizabeth Colbert that talks about us moving into the Anthropocene and more evidence for it. So if we look at geologic and natural hazards, living in certain areas, if you are on those plate boundaries, can increase the risk of hazards to human life, okay, as a result of exposure to earthquakes and volcanoes. So most of it happens around the Pacific Ring of Fire, right? So the Pacific Plate interacts with the North American Plate, the Nazca Plate. It's the South American and the Nazca Plate. It's the Pacific and the Indian Australian Plate. It's the Pacific and the Philippine Plate, okay? So most of these disasters and these hazards exist around the Pacific Ocean. That's not to say that there aren't hazards elsewhere, but these are where the main ones take place. So let's talk about an earthquake. An earthquake is a sudden release of energy at a plate boundary as a result of changes in the tension force on the rocks, and we'll talk about it more in the key points. You can get them in the interior of plates, depending on what had gone on there in the geologic past. As is the case with humans, engineers have come up with ways to protect buildings from shaking. Buildings are designed to be able to move, right? So buildings will bend before they'll break. Okay, like a good tree in the wind is going to bend and move with the wind before it breaks. But this kind of engineering is really expensive, okay? And typically, developing nations do not have building codes like we do here in the United States that make it so that buildings are engineered and designed to be not earthquake proof, but earthquake resistant. Okay, so there was a 2010 earthquake in Haiti that claimed almost 250,000 lives because there were no earthquake engineering codes in place. Whereas there was a bigger earthquake in Chile around the same time. Chile has earthquake engineering codes, building codes, and fewer people died because of the difference in those codes. So here are some of the examples of the big earthquakes in the world. Anchorage, Alaska, 9.2. I remember Loma Prieta. That was the World Series earthquake. Northridge, I remember that one. I remember Kobe. Northern Sumatra was the big tsunami that killed a lot of people. These were the two, Port-au-Prince, Haiti, and Maule, Chile, right? The one in Chile was much larger but caused a lot fewer deaths. And this was the Tohoku earthquake in Japan. So here on the East Coast, our earthquake hazard is low, but we are not immune to earthquake hazards. Out in the West, the building codes tend to be more stringent to deal with earthquake issues. So how to get volcanoes? Volcanoes happen where you have molten rock, ash, or hot gas that comes through the Earth's surface. A lot of times, most of the earthquakes are found on subduction zones where one plate converges under the other. And Japan is the most volcanically active nation, which makes sense because it's on the boundary of the Philippine Plate and the Pacific Plate, which is why you had the earthquakes there. They have about 100 active volcanoes, which is about 10% of the world's total. However, you can have hot spots where lava comes up out of the crust that aren't necessarily connected to plate boundaries. So Hawaii is one of them, right? So the Hawaiian hotspot is right here under the big island of Hawaii. The hotspot stays still, and then the plate moves over the hotspot. So this is the Emperor Seamount chain out here, this vertical piece. At one point, this end of the Emperor Seamount chain was here. So it actually gives you a history of plate movement, even if it's not a direct result of plate movement. And there's actually one under Yellowstone too, which we're going to talk about. Volcanoes can erupt very differently. Kilauea in Hawaii has been blurping lava out pretty much daily since 1983, and people just kind of deal with it. Mount St. Helens, my favorite, put a bunch of ash and cinder into the air and released a pyroclastic flow in 1980. And then you've got Pompeii, right? That was buried by an eruption from Mount Vesuvius in 79 AD. So there's different kinds of eruptions that are determined by the magma and gas content within the volcano itself. And we're not going to get into that because it's definitely beyond the scope of our course. And volcanic eruptions, as we talked about when we talked about air pollution, can release sulfur dioxide into the air and create particulate matter, which then prevents, it creates aerosols which block the sunlight, which then reduces global temperatures. And it happened after Mount Tambor erupted in 1815, and it happened to another degree after Mount St. Helens erupted in 1980, which we'll talk about when we talk about the key points. Landslides are also a form of what we call mass wasting, when you have a lot of material that moves downhill, in a lot of cases due to being saturated, okay? And it commonly affects unstable hillsides. It happens a lot in California. You've got wildfires that burn down a lot of the vegetation, so then there's no roots to hold the topsoil in place when that happens, and you get a lot of rainfall as a result, down the line, as is like the monsoon seasons out there. Those bare hillsides will then become saturated, and you get landslides and mass wasting happening. We talked about tsunamis when we talked about Fukushima Daiichi. We'll talk about how they happen a little bit more in the key points, but when you have big earthquakes, it's very in subsurface ocean earthquakes that originate on the seafloor. You are worried about a tsunami. So the one in Japan was triggered by a really big earthquake, and that's some of the damage as a result. There was one in Indonesia in 2004 that killed over 225,000 people. And it was a thing because it killed so many people because they didn't have a warning system. Now the Indian Ocean has a warning system. One way that we can reduce the impact of tsunamis is to restore coastal ecosystems like marshes and mangrove forests to prevent any issues related to tsunami damage. Those natural ecosystems can absorb some of that energy. So we can make decisions that wind up making these natural hazards more hazardous to humans. So if we live in an area that's prone to hazards, such as a floodplain, we're going to be susceptible to flooding. If we live in coastal zones near plate boundaries, we're going to be more susceptible to tsunamis. If you change the flows of rivers, you're more likely to get flooding. If you clear cut forests on slopes, right, like I had spoken about with California, you're going to set the stage for more mass wasting, right? And because we are exacerbating natural climate change, we are making some of these situations even worse. If we make smarter decisions, and then we have the ability to engineer solutions, that can also help minimize our risk. Okay, so there's a brief introduction to geology.